Now we study more about groups, various aspects of groups, and here's our first lemma of the day. Let's say we have element A of a group G. Then for this given element A, let's define this set C G of A, which is defined by all elements of G such that x inverse A x is equal to A. Okay, then this set is a subgroup of G containing A. A is this element. Okay. So what does this mean? X inverse A x is equal to A. So if we multiply both sides of this equation by x from the left, then we have x inverse ax x a. So this part will cancel. So we have ax is equal to xa. So in other words, this means all elements of G that commute with A. Okay, so this is what defines this set CG of A. Then we want to prove that this is a subgroup of A. So let's prove this. Of course, we want to use the subgroup criterion. But before that, we need to check that this set is non-empty. Okay, and this is easy to see because A inverse A times A is equal to A, right? So this and this will cancel, so we have A. So that means, therefore, A is an element of this set, CG of A. Therefore, this set is non-empty. Okay, now we check the subgroup criterion. First, we need to check that the multiplication. So this set is closed under multiplication. So let x and y be two elements from this set. Then this means x inverse A x is equal to A and y inverse A y is equal to A, because that's the definition of this set. Okay, and then we want to show that x, so what we want to show is xy belongs to CG of A. Okay, so to show this, we need to show xy inverse A xy. So we need to show that this is equal to A. Okay, so let's see. So xy inverse is y inverse x inverse, as we have seen before. But now look at this part, x inverse A x, that is equal to A using this. But now we have y inverse AY, which is equal to A. So therefore, xy belongs to CG of A. So this set is closed under multiplication. And next, we want to show that x inverse also belongs to this set. Okay, I mean, of course, I'm assuming x belongs to CG of A. Okay, and suppose x belongs to CG of A, then we have x inverse A x equal to A. Now multiply x from the left and X inverse from the right. So X X A X inverse. Now this left hand side is from here X times X inverse, so they will cancel. X times X inverse, they will cancel. So the left hand side becomes A. And of course, X is the inverse of X inverse, right? So therefore, from this, we have A equals to X inverse inverse times X, A times X inverse. Therefore, X inverse belongs to CG of A. So this completes the subgroup criterions. Therefore, CG of A is a subgroup of G, and it contains A. And we are done. So let's give a name to this subgroup. So here's the definition. So this subgroup defined as this. So all elements of G such that it commutes with A. Such that it commutes with A. So this is called the centraliser. Centraliser of A in the group G. So A is this A. Okay. And you should note that the group G need not be abelian. Okay, so not all pairs of elements commute with each other. But as long as the centralizer of A is concerned, all elements in the centralizer commute with A. So that's what this means. And also, if you remember, we have defined something similar before, which was written Z of G, that is defined as all elements of G such that for all elements in G, X inverse A X is equal to A. So this compare this. This is called the center of G. Center of G. And on the other hand, this is centralizer of A in G. Okay. So here we have one special element given here. One special element A. This is given. And this centralizer consists of all elements that commute with that special element A. But in the case of center of G, there's no special element. Okay, so it consists of all elements of G such that that commute with all other elements of G. Okay, so here's for all X in G. So this is the important difference. Okay, so don't confuse these two subsets. By the way, so this is called center of G, and we didn't say this is a subgroup, but in fact this is a subgroup. So here is a theorem. The center of G is a subgroup of G. So let's prove this. And you should prove that this is non-empty first, but I will leave that as an exercise. And now suppose we have x and y that belong to the center of G. Okay, so that means x and y, they commute with all elements of G, right, by definition. So that means x, y, and y belongs to the centralizer of A for any A. For any A in G. Right? Because x and y commute with anything, any element in G. So that means if we pick any arbitrary element in G and make the centralizer of that, then x and y should belong to that centralizer because x and y commute with A. So that means x, y belong to the centralizer for any, maybe I'll just write for all A in G. And also x inverse is an element of CG of A because we have shown that the centralizer of any element is a subgroup of G. So these two relations hold for any element A. That means x and y, xy, and x inverse, they belong to the center of G. So this means the center of G meets the subgroup criterion. Therefore, the center of G is a subgroup. Of G. And we are done. Now let's define some more new concepts. As a definition. Let's say x and y are non-empty subset of G. And let's see. X and y are subsets of G. G is a group, of course. And we define xy to be the set of elements consisting of the products like x and y, where lowercase x belongs to this uppercase x and y lowercase y belongs to uppercase y. And similarly, we let's say if we have another subset Z, the xyz is defined as this. And in particular, suppose x, wait a minute. X is a subset consisting of only one element. Instead of writing like this, let's say y, we write just x, y. So we just omit these curly brackets to mean this. So this is the set of all products between x and y, where y is elements of this set, subset y. And similarly, if z is a subset consisting of only one element, then instead of writing like y and z like this, we just write y z. So just omitting the curly brackets. And we mean y z, and y is an element of y. And also, let's say x and y are subsets consisting of one element each. Instead of writing like this, we write x, y, and z to mean this subset. Okay. Now, you should note the following fact. Let's say a, b, x, and y are subsets of a group G. And we assume that A is a subset of B. Okay, in that case, xay is a subset of xby. And you should try to prove this. So if this, then this. And also, if H is a subgroup of G, not just subset, but subgroup, of G, then in that case, for all elements of H, we have this element H times H is equal to H. H is equal to H. So you should verify that. I think this is pretty much trivial because H is an element of this uppercase H. So and this uppercase H is supposed to be a subgroup, so it's closed under multiplication. So if you multiply an element within that subgroup, then it will not go out of that subgroup, so it stays the same. But anyway, you should try to prove this. Now, here's a lemma. Suppose H is a subgroup. It's not just a subset, it's a subgroup of G. And let's say X is any element of G. And then X inverse HX, which is defined as X inverse H and X, where H is an element of H, is a subgroup of G. Okay, let's prove this. Of course, we apply the subgroup criterion. So suppose A and B are elements of this subset. Then what this means is that there exists some elements, say H and K, in the subgroup H, such that A is equal to X inverse HX and B is equal to X inverse KX. Okay? Because that's what it means to be elements of this subset. Okay, now A times B is equal to A inverse HX and X inverse KX. And using associativity, these will cancel. So X inverse HKX. So this means, of course, this H and this K is elements of the subgroup H. So this means HK is an element of H. Therefore, this one belongs to X inverse H X. So this subset is closed under multiplication. And A inverse is X inverse H X inverse. This is X inverse, so we change the order and take the inverses. And X inverse is X. So of course, again, this H inverse is an element of H, so this means this belongs to X inverse H X. So these are satisfied. So according to the subgroup criteria, therefore X inverse H X is a subgroup of G. And we are done. Now, based on this lemma, let us define some new notions. Here's the definition. And let H be a subgroup of G. And any subgroup of, as we have seen, for X inverse H X for some X, which is an element of G, is called, so this subgroup is called conjugate of H. Okay, and if this H, the subgroup H coincides with all its conjugates, so that means if for all X in G we have X inverse H X is equal to H. So if this is the case, then H is said to be normal, or it's a normal subgroup in G. Okay, so for all elements in G, if the conjugate of H is equal to H itself, then this H, subgroup H, is said to be a normal subgroup in G. Okay, and of course, what this means is same as Hx equal to Xh. Okay, so what does this mean? So for all X in G, we have this. So what's the meaning of this normal subgroup? So what this means is that so some elements of Hx can be expressed as H times X, where H is in H, and Xh is set like X times H, where H is an element of H, right? But it doesn't mean we have Hx is equal to Xh for some H in H. So this is not the case here. Okay, we are saying these are equal as sets. Okay, so it doesn't mean each of the elements are equal. So we just happen to be using the same symbol H here, but they may not be corresponding to the same elements. So what we mean by this is for some elements H and K, elements of the subgroup H, we have Xh equal to Kx. Okay, so this is, so there is always some elements such as H and K with which this equality holds. So that's what this means. The normality means here. Okay, so this is a kind of relaxed version of commutativity. So this doesn't exactly mean commutative. Okay, so H and X, all elements in X and all elements in G, they do not commute in general. So it's a little bit more relaxed version of commutativity. And this definition of normal subgroups can be relaxed to some extent according to the following theorem. So again, H is a subgroup of G then H is normal. Normal means this, okay, or this. If and only if for all x in G we have x inverse H, x is a subgroup of H. Okay, it doesn't have to be equal. Okay, so this is a theorem. So let's prove this. Since this is if and only if statement, we have to prove both directions. And first, let's prove only if part. So suppose H is normal. Then this implies that by definition, H is equal to x inverse Hx for all x in G. Okay, so this in particular implies that so if two sets are equal, that means the left hand side is a subset of the right hand side, and the right hand side is a subset of the left hand side. So in particular, this implies that x inverse Hx is a subset of H for all x in G. So we are done. And conversely, suppose we have x inverse Hx is a subset of H for all x. Then if we multiply both sides by x from the left and by x inverse from the right, we have this x H x inverse, and this will cancel, this will cancel. So H is a subset of x H x inverse. But now x can be expressed as y inverse for some y in G. So this can be written as y inverse H y. So this is the same form as this one. So to get, but these letters doesn't matter whether we use x or y. It doesn't matter because it's for all x in G. So if we vary x for every element in G, then y varies every element in G. So together with the assumption, this and this, then it means H is equal to x inverse x Hx, where x is any element for all element in H. Therefore, H is normal. Normal. And we are done. Now let's see an example. This is the Cayley table of the dihedral group of order 8, which we have seen before. So there are 8 elements, and the multiplication table is given here. And for this group, so it's called D4 by the way, the center of this group is ZD4. This is actually E and B. So the center of this group consists of these two elements. So to to confirm this, we need to check that these two elements are central elements of this group. And E is the identity element, so it is trivial that this is central. So let's see if B is indeed a central element. To check this, we need to examine uh, these things. So A inverse BA is equal to B. Is it true? So A inverse is what? So A inverse is so A times C is the identity element. So A inverse is actually C. So C times B is A. So that's AA. So A times A is B. So this is okay. And obviously B inverse B times B is of course B because they just cancel. What about C inverse B C? And C inverse is A, as we have seen before. So A B C, and AB is C. So this part is C, so CC, and C times C is B. So again, this is okay. And D inverse B C B D. So D inverse is D. So DB is G, and GD is B. GD is B. So this is okay. And F inverse B F. F inverse is F. So FB is H. So H F, and H F is B. And G inverse B G. G inverse is G. And GB is D, and DG is B. And H inverse BH, H inverse is H. And HB is F. And FH is B. So for all elements, that element inverse times B times that element is equal to B. So therefore, the element B is indeed central. And if you check all other elements like this, they will never satisfy these conditions. Okay, so these two elements are the only central elements of this group. Therefore, this is the center of D4. And as you can see in the definition, from the definition, any center, the center of any group is always a normal subgroup. Okay, but not the other way around. Not all the normal groups are the center of a group. So there can be more normal groups than just the center of a group. And for this dihedral group of order 8, D4, there are other subgroups of order 2, but these are not normal. For example, we have subgroup ED, as we have seen before. For this one, if we multiply A inverse and A, we have A inverse E, A, and A inverse D, A. And that is E, and A inverse is C. CDA, and CD is H, HA, and HA is G. G, which is not equal to this. Therefore, this subset is not normal. And for this D4, the group D4, there are 3 subgroups of order 4. And it can be shown that all of them are normal subgroups. For example, we have this group, E, B, D, G. So among all these 8 elements, E, B, D, G, so they comprise a subgroup of D4. And we can show that this is a normal subgroup. For example, if we multiply this one by A inverse from the left and A from the right, then we have, so just calculate all of these products, A inverse BA and A inverse D A inverse GA. So this is just E, and A inverse is CBA. So CB is E, and E times A is A. And so A inverse is C. Okay, so CDA. CDH times A is G. So we have G here. And CGA. CG is F. F times A. F times A is D. So we have D here. So that is E, A, G, D. E. Oh, wait a minute, something is wrong. Okay. Wait a minute. BA. BA is, I think, BA. BA. It's C. Okay, sorry. Wait a minute. CB. Okay, CB is A. Okay. And CB is A, and A squared is B. Okay, so this should be B. Okay. Anyway. So EBDG, of course, for sets, the order doesn't matter, so these two are the same sets. And you can do the same thing for all other elements, B, C, D, F, G, H, and so on, and you still have the same result. Therefore, this subgroup is a normal subgroup. And by the way, all the subgroups of order 4 are the following. So this is one thing. And others are E, A, B, C. And the last one is E, B, F, H. Okay, so there are these 3 subgroups of order 4 for the group D4. And all of these have E and B in common. So if we take the intersections of any of these any two of these 3 subgroups, then we have EB as the common elements. And of course, as we have seen, the intersection of 2 subgroups is again a subgroup. So of course EB is a subgroup. And what else? Okay, so we have the following. So ED is a subgroup, and if we take A inverse times this subgroup and A, then we have A inverse EA and A inverse DA. That is E, and CD. CD is H, and HA is G. HA is G. Yeah. So this and this are not equal. However, this and this are conjugate to each other, right? Because they are related by this operation. Here's the next theorem. Suppose H and K are normal subgroups of G. Then H cap K is a normal subgroup of G. Okay, previously we have seen that if H and K are subgroups of G, then H cap K is also a subgroup, right? But here we also impose this condition, normal subgroups. So normality is also preserved if we take the intersection. That's what this theorem says. So let's prove this. And about subgroup part, we have already shown. So what we need to show is the normality part. Okay. So let's see. Let X be an element of G, and from H cap K is a subset of H. So if we multiply both sides by X inverse from the left and X by X from the right, we have X inverse H cap K X subset X inverse H, but H is supposed to be a normal subgroup, so this is equal to H. Okay, and also H cap K is a subset of K, so we have a similar relation. X is a subset of K, so we skip something similar to this one. So we have this and we have this. So what this means is, so if we have H and we have K, so this, okay, this thing is completely included in H. So something like this, say. So there's nothing outside of H, okay? But this one says this thing is completely included in K. But since it doesn't go out of H, so it should stay here. So there are no such part as this one. So everything is inside the intersection. So what this means is X inverse H cap K X is a subset of H cap K. And from the previous lemma, this implies this implies that H cap K is a normal subgroup. And we are done.